So folks, in this problem we're asked to express the surface area as an integral. We're not going to solve that integral. We're asked to set it up. So I'm going to do a review of how to find surface area. If you feel comfortable with how to find surface area and want to jump straight to the calculation, here's the timestamp for that. Anyway, as a reminder, the integral for surface area is simply the double integral over S ds, which should look very similar to our area integral when we said that was the double integral over R dA, but where we thought of R as living in R2, this surface lives in R3. So this is our statement for the surface area of a surface, but it's not a very practical calculation. So instead, we're going to suppose that R of t describes the surface, R of u and v, so it's a vector valued function that maybe it looks like f of u and v and g of u and v. Well, if that's the case, and let's go ahead and give some time parameterizations on this, we'd have a less than or equal to u less than or equal to b, and c less than or equal to v less than or equal to d. Then we can go ahead and give the surface area in terms of this parameterization of this surface. So this would be the integral. We'll start with the u as the outermost integral, so the integral from a to b, the integral from c to d, and then what we have here is the magnitude of partial r partial u crossed with partial r partial v, and we'll take that with respect to first, I guess, v and then u. The only other thing to say is that this is assuming that we've got a nice rectangular region in our uv space for our parameterization, but in reality one of these may be functions like we saw in some of our other double integrals, and that will be the case in this problem. So with that as a guide, let's go ahead and tackle this problem. So in order to tackle this, we need to have a parameterization of our surface. Unfortunately, I'm looking at our surface here, y cubed cosine squared x minus 1, and I can't think of any nice coordinate system to put this into. There may be one, but I'm not sure what the graph of this looks like, and I'm not sure how I can utilize the symmetries in the graphs of this surface to try to simplify the integral. So I'm going to do a very standard parameterization then. We're just going to say, let's let r of uv be the coordinate functions, and then we'll just let u be the same thing as x, v be the same thing as y, and we'll let z be that the original expression of our surface, but with u and v replaced. So we'd have u cubed cosine squared v minus 1. So if you want me to state out the substitutions explicitly, we have that u is equal to x, and v is equal to y, and z is just equal to, or excuse me, then z would just be the original expression in terms of x and y. The next thing we need to do is we need to look at our boundaries of our parameterization, and so for that we need to graph the original region in xy space and then look at what it must look like in uv space. Of course, what we sketch in xy space will be the same as what we sketch in uv space, because in this case we're just using the standard parameterization. So here I've gone ahead and sketched the region in both the original space, xy, and of course, because we're just using a standard transformation here, or the kind of the natural parameterization, then we have the same space for u and v. So now we can go ahead and describe this region, and I'd like to describe the region. Let's go ahead and label it, I guess. We'll go ahead and label it as R. And R in the uv plane. There's lots of ways we could write it. I'm going to choose to write it this way. It's a set of ordered pairs u and v, such that, and then I'm going to choose to say that my v values range between 0 and 1, or excuse me, 0 and 3. The v values are ranging between 0 and 3, and the u values are ranging between 1 and then wherever it hits this line. So I'm choosing, when we go to integrate this, we're going to integrate the region as these green lines. So we can see the u values will run from 1 until whenever we hit this curve right here. So let's go ahead and describe this boundary line right here. So one way to say that is the boundary line v equals u minus 1. But because I want to integrate with v being the outer integral, we'll write this as u is equal to v plus 1. So we have that our u goes between 1 and when we hit that curve, which we're saying is the curve v plus 1. So now I've described this region, and now we're ready to jump into computing the cross product of the partials. So let's go ahead and do that. So again, we had the parameterization r of uv and so we can go ahead and take the partial derivative of that with respect to u, and when we do so we get 1, 0, and then we would have minus 2 v cubed cosine u times the sine of u. And when we take partial r partial v, we end up with 0, 1, 3v squared cosine squared u. And so now we're going to go ahead and compute the cross product of those two. So partial r partial u crossed with partial r partial v. That is, let's give ourselves some room. I, j, and then k is going to need quite a bit of room. And so then we would have 1, 0, and minus 2 v cubed cosine u sine u. And then the second vector we have is 0, 1, 3v squared cosine squared u. So let's compute that cross product. So you can check me on that, but there's the cross product. And then we want the magnitude of that. So at this point we now have all the components to compute the surface area. So we're taking, in this case we'll say that the surface area is equal to the integral. And then we want to, based on our choice of describing this circle, we're going to use v as our outermost integral. So v is going to go from 0 to 3. Our innermost integral is going to be u. We said that u is going to go from 1 to v plus 1. And then we have our integrand, which is the cross product, the magnitude of that cross product. So 4v to the 6th cosine squared u sine squared u plus 9v to the 4th cosine to the 4th u plus 1 du dv. That's a v. Folks, take a look at that and let me know if you have any questions, and we'll move on.